Okay, in this video, I'm going to look at recurrence relations of Legendre polynomials. We just note that this term is synonymous with these can also be called recursive formulas or recursion formulas as well. Or recursion formulas. So either of these terms carry the same meaning. Right. What are recurrence relations? Well, these are formulas that relate polynomials of different degrees. Okay, so they give a relationship between polynomials of different degrees. So then naturally these formulas can be used to find higher degree polynomials if the lower degree polynomials are known, so they can be used to find higher degree polynomials from the lower degree polynomials. So instead of say using the generating function repeatedly to go maybe to degree 4, then we can, since we say for instance now P2, then we can use these to find P3, etc. All right. Here we're going to present just the three basic recurrence relations of Legendre polynomials, and then we can work with these ones to derive others where necessary. So just the three basic recurrence relations of Legendre polynomials. The first one says n plus 1 pn plus 1 of x is equal to n plus 1 xpn minus n times pn minus 1 of x. This is going to be true whenever n is 2 or greater. Then the second recurrence relation is xpn prime minus pn minus 1 prime is equal to npn. Note that for brevity was just typically going to write this as pn, but we know all the time that of course these are functions of x. And then the third one is 2n plus 1 times pn is equal to pn plus 1 minus pn minus 1 prime. So these are the three basic recurrence relations for Legendre polynomials. Okay, now so notice for instance that we could use this first one to calculate higher degree Legendre polynomials. If you set n to be equal to 2 here, then this is going to be P3. then this is going to be P2, which we know from our previous calculations. This would be P1. So that means we can use P1 and P2 to calculate P3, and then once we know P3, we can use P2 and P3 to calculate P4, etc., etc. Okay, now we're going to see how the recurrence relation 1 can be derived. So in the next section, we're going to look through a derivation of recurrence relation 1. We are going to work from the generating function. So gx of h, g of x and h is 1 over square root 1 minus 2xh plus h squared. This is equal to h to the power n times pn, and runs from 0 to infinity. So what we want to do here is we are going to differentiate partially with respect to h. Okay, differentiate partially with respect to h. We're just going to work with these two here. So derivative of this with respect to h is going to be minus 1/2. Then the derivative of this is going to be 2h minus 2x. So 2h here minus 2x, and then so when we subtract 1 from that power, this is now going to be power 3/2. And then on the right hand side, when we differentiate this, we are going to get n times h to the power n minus 1. That means our lower summation index is now going to have to start from 1, because when n is 0, this whole thing is going to be 0 here, right? Then simplifying on the left hand side, so we just have x minus h all divided by now power 3/2. We can write that as square root 1 minus 2xh plus h squared, and then we multiply that by 1 minus 2xh plus h squared. But what we're going to do is we're going to take this term to the right hand side. So then our equation is going to look like this. Then summation of n times h to the power n minus 1, n from 1 to infinity. Then on the left hand side, we're going to recall that 1 over square root of this is equal to that summation. So we are going to replace we're going to replace 1 over that using the summation. So we're going to have here x minus h into summation from 0 to infinity of h to the power n times pn. This side we already have that, of course. And then at this point, we are going to multiply into the summations. Going to multiply into the summations. So this does not depend on n, so we can multiply this as well. Similarly here, all these terms do not depend on the dummy variable, so we can multiply them into that. So on the left hand side, we're now going to have two summations. The first one is going to be summation from 0 to infinity h to the power n xpn. So just multiply it x into that summation. Then in the second case, we're going to multiply h, so this power is going to change to n plus 1. And then on the right hand side, when we multiply the summation by 1, it's going to remain exactly as it is now. Okay, and from n equals 1. Then the second term, we're going to multiply by minus 2xh. So we're going to have 2n h, the power is now going to be n, then x times pn, and goes from 1 to infinity. Then the last term, multiplying h squared into the summation, we're going to have nh to the power, going to be n plus 1 now, p of n, and sums from 1 to infinity. All right, now as is standard with these calculations, so at this point, the first thing we're going to do is we're going to equate the powers of x, and then after that we equate the lower summation limits. So here we're going to equate, I'm going to write this in inverted quotes, the powers of h. So we want to let our target power to be h to the power n. So that means this one is already okay. This one is already okay. The other three, we need to manipulate the power of h. So remember, power of h is a dummy variable. Okay, so whatever we call it is not an issue, whether it's m or n. What we get ultimately is the same thing. So this one has got n plus 1. So what we're going to do is we're going to let n plus 1 to be a new variable m. This one has got power n minus 1. I'm going to let n minus 1 to be a new power m. For the last one, we're going to do the same thing as with that first one there. So n plus 1 must be equal to m there. Okay, then let's rewrite this and see what we get. So the first term is the same as before. So we have got h to the power n xpn. N is running from 0 to infinity, minus, now in the second term, so here we go. So our new power is now m. So we're going to have h to the power m. Now, if we make n the subject of the formula here, n is going to be m minus 1. So pn is the same as pm minus 1. And then the lower summation limit, when n is 0, m is 1. So our lower summation limit is now going to be m equal 2, 1. Okay, something similar is going to happen here because we've got exactly the same substitution. Now let's go to the first term on the right hand side. So this time n minus 1 is m. So it's going to be m. From here, n is m plus 1. So we're going to have summation of m plus 1, h to the power m, pm plus 1, because n is m plus 1. And then for the lower summation limit, when n is 1, m is 0 for this term. So our lower summation limit now is going to be m equal to 0. Okay. The second term remains exactly as it was before. We have got 2xn h to the power n pn. Lower summation is 1 limit. And then the last term, we're going to have to do a manipulation similar to what happened to this term here. So here n is m minus 1, so that's going to be m minus 1. This is m pn minus 1 there. When n is 1, m is going to be 1 plus 1, m is going to be 2. So this time we're going to be summing from m is equals to 2. N is m minus 1, so m minus 1 here. H to the power m pm minus 1. So that is sorted. The powers are now the same. Now remember, we could as well just replace this by n now, because n or m, these are dummy variables. Okay, so after this, we're going to equate the lower summation limits. So typically we browse through the lower summation limits and look at the largest, and then we're going to have to make all of our summations start from that one. So in this case, we're going to have to make all of them start from 2. So that is easy to do. So this one, for instance, we evaluated at 0, evaluated at 1, then let the summation start at 2. This one we evaluated at 1, and then the summation starts at 2. Once the power of h and the lower limits are the same, then we can factorize this. We can write all of them as one summation. So, well, maybe in this case we have one summation on the left hand side and one summation on the right hand side. So let's get going. So this time we are going to equate the lower summation limit. So this time we're going to make sure that all the lower summations start at 2 by evaluating if necessary. All right, so as I've already mentioned, for the first one here, we're going to have to evaluate this for n equals to 0 and n equals to 1. When n equals to 0, this is going to be 1, so it's going to be x p naught. So we're going to have x p naught, so that's n equals to 0. And n equals to 1, we're going to have h x p1. Okay, going to write the x first, p1, and then the rest of the summation is now going to start from 2. Then we evaluate this one, excuse me, at m equal to 1. So it's going to be h p naught. Okay, so minus h p naught. And then what we can do now, the summation on the left hand side, we can use m, we can use n, doesn't really matter. I'm going to use m. So both of them are going to start from 2, and the power of h is going to be the same. So we can combine these two and write this as simply the summation of x pm, which is simply this, minus pm minus 1, and then all of these terms are times xh to the power m. Okay, then we're going to do the same thing on the right hand side. So evaluate this at 0 and 1. So at 0 it's going to be just p1. So we're going to have p1 at 1. This becomes 2. That becomes 2. That becomes 1. So it's 2h p2. And then we're going to be good there. This one, the next one, we need to evaluate this at n is 1. This one is already starting at 2, so that's fine. When n is 1 here, it's going to be 2x hp1. So minus 2x hp1. And then the 3 of those summations now we can group together. They're going to be m plus 1, pm plus 1 from this term, and from this term we're going to have minus 2x mpn minus 2x mpm, and then from the last term we're going to have plus m minus 1 pm minus 1, then everything is multiplied by h to the power m. Okay, we're almost there now. So next what we need to do is to compare coefficients of powers of h. So we're going to compare coefficients of powers of h. We're going to start with h to the power 0. On the left hand side, the terms involving h to the power 0 is just this one. So we have got x times p naught. On the right hand side is just this one, p1. Now remember, p naught is 1. So here if we express this in terms of the higher degree polynomial, make that one the subject of the formula. So this is saying p1 is x times p naught, which is 1. So this is fine. So this is definitely true. Okay, then we go to h to the power 1. There are going to be 2 terms on the left hand side, this one and this one. I'm just looking for the coefficient of h. So we're going to have xp1 minus p naught. So we've got xp1 minus p naught on the left hand side. The right hand side we're going to have 2p2 minus 2xp1. So 2p2 minus 2x p1. And then again, we express this in terms of the highest degree polynomial here, which is p2. So this is saying s is going to be 1/2 of, if we bring this to this side, we're going to have 3 of those. So 3x p1, we know that p1 is x. Okay. Then that's going to be minus p0. P0 is 1. So this is giving us 1/2 3x squared minus 1, which is true again from our calculations earlier. So that's h to the power 0, h to the power 1. Then we're going to do h to the power m, where m is starting from 2 and going upwards. So that's going to be these terms now. Now, the coefficient of h to the power m on the left hand side is this one. So we're going to have xpm minus pm minus 1 minus pm minus 1. On the right hand side, we're going to have m plus 1 pm plus 1. Maybe let's put this here. So xpm minus pm minus 1, m plus 1 pm plus 1, followed by minus 2x m pm. So minus 2x m pm, then plus m minus 1 pm minus 1, m minus 1 pm minus 1. So then what I'm going to do is I'm going to take these terms here to the left hand side. So when we do that, we're going to have xpm, which is this term here, plus 2xm pm, which is this term here, then minus pm minus 1 minus m minus 1 pm minus 1. Then we're going to have m plus 1 pm plus 1, which is this term here. These two terms are going to combine to 2m plus 1 xpm, and these two terms here are going to simplify to minus m pm minus 1, and then we've got m plus 1 pm minus 1 there. Okay, and so of course this is going to be true for m is 2 or greater, and this is of course the required recurrence relation. So that's the derivation of the first recurrence relation. We're going to go to the derivation of the second one now. All right, in the case of derivation of R2, what we do is we differentiate the generating function with respect to x this time. Remember, in R1 we differentiated with respect to h. When we differentiate with respect to x, the left hand side is going to be h over 1 minus 2xh plus h squared all to the power 3/2. The summation term is going to be h to the power n Pn of x prime. Now, since the derivative of the p naught term is 0, so p naught prime is 0, our lower summation is going to have to be n equal to 1. Then from the R1 derivation, the term, this one, 1 over 1 minus 2xh plus h squared to the power 3 halves, we can write like this. I'll just scroll up in a moment to show you where we're getting this one. Okay, so remember when we differentiated here, yeah, so yeah, here, so if we just I'm just going to tidy this up here. So this is simply x minus h here. Now if you take this term to the other side, then we're going to have 1 here and 1 over x minus h there. So that's what we're talking about. So that term is equal to that. Now we have that term, so this term we have it here. Okay, so we're going to simply replace this by that. Okay, so and hence so we are going to have just one moment here. Yeah, so we're going to have h over x minus h into the summation of that equal to this on the right hand side. Okay, then all we do is we're going to take this term and bring it to the right hand side. So we're going to have h into n equals to x minus h, h to the power n. So in both cases, n is summing from 1 to infinity. Then multiplying into the summation terms, the right hand side becomes nh to the power n pn. On the right hand side, we're going to have two terms. One of them is going to be h to the power n xpn prime. The other one is going to be h to the power n plus 1 pn prime. N starts from 1 to infinity. Then the only term that needs sorting here in terms of the powers is this one. So we're going to let n plus 1 to be equal to a new term, m. Then when we do that, this side is going to remain the same, which is the left hand side, n equals to 1. Remember, whether I write n or m, it's immaterial really, because it's a dummy variable. So that's going to be n h to the n pn. This one again remains the same, h to the power n x pn prime. And then this one, we're now going to be writing it in terms of the dummy variable m. So h to the power m Pn becomes Pm minus 1 prime. When n is 1, m is 2. Okay. So then again, we are going to need to equate the lower summation limit. So evaluating this term when n is 1 is simply going to give us h p1. Okay, and then plus that term, now summation term, summing from 2 Pn, evaluating this one when n is 1 is going to give us xh p1 prime. Then these two terms we can now combine because they are both summing from 2. We use n. They're both summing from 2. So we're going to have h pn prime minus pn minus 1 prime h to the power n. The xpn is from there and the pn minus 1 is from there. So, and then again, if we compare the powers, what's going to happen is that the h to the power 1 terms again agree, because this one is just x, and this one p1 prime is 1, so again it's just x, so it's just saying x is equal to x. So, and then when n is equal to 2, coefficient of h to the power n this side is npn, coefficient of h to the power n this side is x pn prime minus pn minus 1 prime. So that means that is going to be our second recurrence relation. Of course, it's applicable when n is 2 or greater. Alright, so thanks for watching. Hopefully this has been useful. Please do subscribe and make your comments. If you've got questions, you can post them in the comments section. Thank you.